Hello everyone, my name is Sarp Joshkun. Let's talk about the activation functions. We have seen ReLU function being applied in hidden layers within the hidden units. So let's talk about what is ReLU. ReLU stands for Rectified Linear Unit. And if you would like to represent it in a graph here, I'll put positive infinity, negative infinity. And in this plot, it will be a linear unit where I'll just use red here on this side of the positive values, and it will be zeroing out on the negative values. So this will give a simple function that is, first of all, computationally efficient. Okay, I'll just say it here, computationally efficient. And two, it is simple to implement. Simple implementation. And basically it's just max of 0 and x is y, right? So it's a very simple formula here. And the third will be helping with the addressing the vanishing gradient problem, which we will talk about later. Okay. So ReLU is very commonly used in the hidden layers. But there are other activation functions. Let's think about a real-world example where we have an image. Let's say this is an image of a car here. And we pass this image. First of all, we need to convert it to a vector. Let's say each pixel we convert to a specific number, let's say 76, and then this input vector will be passed into the model. And then model will have an output. Let's assume this is a simple output here. We will have hot dog or not hot dog, okay? So I'm just making an example here. So the real world output will be not hot dog, because this is a car, right? So overall, this problem is a binary classification problem. And in the output layer, we have a probability distribution of two classes. And in order to achieve this, we have an activation function called Sigmoid activation function. So let's write it down here. So I will just say Sigmoid activation function, where we have, I'll put the formula here. Let's say it's sigmoid z is the input, and we will be 1 over 1 plus exponent of minus z. So you can bear with me on this formula. It looks complicated, but it's not. So if we just draw the function here, same way we did for ReLU, I'll put it here. What it does is it creates the probability distribution and squeezes the numbers between 0 and 1, right? In here, let's assume we put x as 0, right? When x is 0, which in this scenario will be the exponent 0, which will be 1. So 1 over 1 plus 1 is 0.5. So you'll be passing on the 0.5 here. And if we go to negative infinity, let's say, and then positive infinity here, then the exponent negative infinity will be exponent infinity. that will be infinity. So 1 plus infinity will be infinity. 1 over infinity is 0. So what will happen is we're looking for some kind of a parabolic shape like this. And this will be 1, and this will be 0.5. Okay? So the values will be squeezed into the 0 and 1 as a probability, because this is a binary classification. And if our model was, let's say, a multi-class classification, then we would be expecting more classes here. Let's say, I'll just say here again, maybe 0.96, 0.001, dot, 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 dot. And we can say this is a car in this scenario. And we have other objects here too, but this is a car image. For this, we can use a softmax function. And the softmax function will normalize the output of our network to a probability distribution over predicted output classes. And that's another activation function we use. So as you can see, there are multiple places that you can use activation functions. Now let's talk about the loss function itself.